Okay, in this video we're going to look at Hooke's law for an ideal spring. So you guys derived this from part one of the spring lab, that the force that a spring exerts is dependent upon the K, which is, let's remember this is the spring constant. The units are newtons per meter, and it's a property of the spring. Really a measure of the spring stiffness. So the higher the K, the stiffer the spring, the more force it's going to take to stretch it. Let me get this on the screen here. And then delta X is our displacement, our stretch. So the key takeaway from Hooke's law here is notice that all of a sudden F sub S, the spring force, is not constant. It varies according to displacement. And it's also negative. So now why is this negative? Why is the spring force negative? Well, let's draw an example of a typical horizontal spring. Now horizontal spring just means it's stretched out on a table or horizontal surface. And it's attached to a mass. We call this a mass spring system because both objects together are acting as one system. And so let's say I stretch this spring with some external force applied to the right. I'm going to apply some force to the right to stretch the spring. Now first of all, where is the equilibrium position? Equilibrium for a horizontal spring will occur when it's unstretched. So at this spot here, let's call this x sub naught. The x sub naught unstretched length is my equilibrium position for a horizontal spring. At this position, the spring is not stretched, therefore Fs is 0. Now, if we look at applying a force to stretch it to some displacement away. So I'm holding it at a new equilibrium where the applied force is balanced now with the spring force. So I pull on this mass, the mass pulls the spring's pulling back on the mass in the opposite direction. So notice here, my displacement, delta x, was positive to the right. The spring force, F sub s, is negative to the left. So since these oppose each other, I account for that in Hooke's law. Fs is equal to negative k times the displacement. K delta x, or sometimes you just see it as kx. Now in this case, the applied force is in equilibrium with F sub s. I have a new equilibrium, but the equilibrium I'm talking about here for a horizontal spring is when there are no other applied forces. Now, how can we use Hooke's law to find the equilibrium position of a vertical spring with a hanging mass? So now, this is similar to the system that you guys created in the lab, where you had a spring and it had its unstretched length. And then you attached a mass to it, and that mass stretched the spring. You know what, I'm going to draw the mass here. Assume at this point you're just holding the mass up, so the spring's at its unstretched length, just for purposes of getting a reference point. And then you let it hang, and it hangs at rest. And this is a new equilibrium. Or we would say equilibrium for a vertical hanging mass system. This is mass spring system. Okay, so if we look at the forces on the hanging mass at equilibrium, so let's look at the free body diagram. So we have the force of gravity on the hanging mass, which will be m times g. And then we have the spring force that's pulling back up on that object, and this is going to be negative k times delta x. And these must be in equilibrium, since I must have a net force of 0 if the acceleration of the mass is 0. Okay, so now my delta x is measured from here down to here. So relative to this system, when we look at some of the forces in the y equals 0, I have an upward force of Fs. So Fs is negative relative to the displacement, but in terms of my free body diagram, I'm looking at the magnitude. It's in the positive direction. So my displacement here is negative, my Fs is positive, so it's opposite the direction of displacement, in this case, positive. And then relative to this reference frame, gravity is downward. And these two must be equal to each other. So since the magnitude of F sub s is k delta x, that's a tongue twister, F sub s. The magnitude of Fg is mg. We get that k delta x is mg, or if I divide this by k, the delta x, the stretch at equilibrium, is mg over k. So this is the vertical stretch of a hanging mass system at equilibrium. And that's a way you can use Hooke's law to find that property for a vertical hanging mass system. And that's a recap of Hooke's law.